Hi. When we finished dynamic economic analysis, the last topic came from chapter 15 from Jiang, right? And was associated with first order differential equations. We did them in pretty much extreme depth, of course for the purposes that we needed, applications to economies. And assuming that you appropriated this material well, we are ready to go one step further. So what first thing we're gonna cover over here is what starts in chapter 16 in Jiang, and those are linear differential equations. Well, this is linear differential equation of order n with constant coefficient and constant term. Look, this is an example of such an equation. So look, what do we have over here? So this, of course, is an equation. Here we've got a constant term, right? B is just a constant, right? Not much to talk about. Then we've got y as a function of time, right? And it has also a constant coefficient, some constant coefficient a n. Then we've got first derivative of y with respect to time. So here we basically have dy dt. And again, it's multiplied by a constant coefficient. Here we've got second derivative, d square y dt squared, and a constant coefficient on it. So it's multiplied by some number. And we go on like this until we arrive at derivative of y of order n minus 1 with respect to t. And finally, we've got a derivative of nth order. Now, when you look at that, when you look at this, you see that this is the only one that doesn't have a coefficient, right? So, shouldn't we do a case like this? Well, we could, but look, if we have a general case like that, we can always divide both sides by a0, and we're gonna end up with something in a similar form, but with 1 over here. This is why we prefer this way, because we know that any differential equation like that can be easily brought to this form. And this is the type of equation we are gonna solve in the first part of this class. However, of course, we're not gonna start with this, because this is a very complicated case. We're gonna start with second order linear differential equation with constant coefficients and constant term. Here we should have constant coefficients and constant term. Okay, so basically what we've got over here is that we've got y, a function, its first derivative with respect to time, and its second derivative with respect to time. Okay, so good thing about it is that once we know how to solve this, we've got all the information needed to solve an equation of any complexity. Of course, I'm not saying it's going to be easy, but knowledge about second order differential equation is going to be sufficient for us to deal with this problem. So this is where we are actually where we are actually starting. Now, as you see, I put this t over here everywhere. Why did I do it? I wanted to stress out that y is a function of time, which is the fundamental thing underlying the entire analysis. However, writing it like this would be very time consuming. So look, since this moment on, I'm going to be writing this expression like that. But of course, please remember that here we just have y as a function of time. This is the first derivative of y with respect to time. This is the second derivative of y with respect to time. Okay, so now that we know what we are dealing with, the next thing to do would be, of course, to find a solution to this differential equation. Okay, and of course, just like in the case of first order differential equation, the solution is going to be made of two components. One is particular integral, which represents equilibrium solution. So what is happening when all the forces are balancing each other, when we are in equilibrium? And the second part is the complementary function that tells us what happens if we are getting out of the equilibrium. And in this video, we're going to start with particular integral, so the equilibrium solution, because it's easy, and actually, as you see a little bit later when it comes to complementary function, we're going to have to add a lot of new knowledge. We're going to have to add a lot of new knowledge for us to be able to fully appreciate how those differential equations and their complementary functions work. Okay, so we're going to start with the particular integral. And we remember that this is the equilibrium solution. Okay, so here the solution actually will depend on a specific case that we've got. So let's start with the case number one. The case like this. So in case number one, we've got that A2 is different than 0. Right, when A2 is different than 0, basically what we've got is this. Equals to B. Of course, here we could make additional sub-cases about it, but I don't want to get into details and cloud your judgment here. So let's just move to the solution. I hope you remember that when we're dealing with first order differential equation and we're trying to find a solution, we were using a very specific technique. This technique was to find a trial solution. So we're trying to find a solution by guessing it. But look, if we are going to guess, we should start with the simplest possible case, right? And if we're going to start with the simplest possible case, it doesn't work, we can make it more complicated, but it's kind of pointless to start with something more complicated and get into something simple. So look, in this case, we're going to do exactly the same thing we did previously. So we're going to try the most simple case, that y equal to some constant k, right? So, what do we see over here? Y is constant, right? Here. So, but this means that if I differentiate a constant, I'm going to get 0. If I'm going to differentiate 0, I'm going to get another 0. So now all we have to do is to substitute these results into our equation and see what we are getting. So now, look, instead of YB's, we've got 0. Then we've got plus A1 times 0 plus A2 times K equals to B. So look, what we get out of it is basically those two components are 0. So we've got A2 times K equals to B, which means that K is equal to B over A2. And this means that the particular integral in this specific case is equal to a constant B over A2. With, of course, with the restriction that we imposed at the beginning that A2 must be different than 2. And I hope you can see the resemblance between this solution that we've got over here and the one that we got for a first order differential equation. First order differential equation that we tried previously. There is basically one-to-one correspondence. Before it was B over A, but of course then we didn't have the last component. So, as you see, not much more is added over here. Okay, but look, this result is very nice, but it points us into the next possible case. What if A2 actually is 0? This solution is no longer going to work. So this time we cannot no longer use K, a constant, as a solution. So what should we do in this case? Okay, first let's put it on the blackboard. So we've got case number 2, and in case number 2, we're going to have A2 equal to 0, and this time we're going to assume that A1 is different than 0. Okay, so how does our equation going to look? Look, so we've got YB's plus A1 Y prime, and now look, now we have plus 0 times Y equals to B. So basically, this component completely unnecessary for us, but let me just leave it for you like this. So we see what actually is going to happen. And okay, again we need to start by figuring out a trial solution. Now, look, we know now that the constant solution is no longer going to work here. Because for constant solution to work, A2 would have to be different than 0. So what is the second least complicated function? Of course, a linear function. So we've got k times t. Again, k is a constant. Okay, but then we know that if y prime, first derivative with respect to time will give us just k, and the second derivative will give us 0, right? No surprises over here. So let's now substitute our results to what we've obtained over here. Okay, so we get now that y prime, yb is 0 plus a1 times, instead of y prime we write k, plus 0 times kt equals to b. Okay, we clearly see that those two doesn't matter for anything. So we've got that a1 times k equals to b, which means that k is equal to b over a1. And look, now we've got the second, the particular integral in case of this, in case where a2 is 0. So we've got that particular integral is simply b over a1 times t, because remember, this is where we started. But in this case, again, we need to make this restriction that a2 is equal to 0. However, a1 is different than 0. Now, a1 cannot be equal to 0. Okay, so now that we've got this, what if they are both 0? What if both a1 and a2 are equal to 0? So now we see that if they are both equal to 0, the two solutions that we had no longer gonna work. So let's try the third possible solution. So look, now we've got a case where a1 is equal to a2, and they are both equal to 0. So how does our equation look like? Well, it's simply yb's plus 0 times y prime plus plus 0 times y equals to b. Okay, now we know that this solution also not going to work, so we're going to try the third simplest solution we can get. Okay, the third possible solution, of course, is a quadratic function, right? So we've got y equals k t squared. In this case, y prime is equal to 2kt, and y b's is equal to 2k. So, in this circumstance, we've got, if we substitute those results, we get that this is 2k over here plus 0 times 2kt plus 0 times kt squared equals to b. Again, those two don't matter, right? They're out of the picture. So we've got the 2k equals to b, or k equals to b over 2. And this is how we get our third possible solution, that particular integral in this case is equal to b over 2 t squared, right? But of course, we make restriction here that both a1 and a2 must be equal to 0. let's summarize what we get, what we got. Look, basically, we can have three possible cases when we are looking for the particular integral in case of the second order differential equation with constant coefficient and constant term. Okay, so now, if equation goes like this, so we've got y plus a1 y prime plus a2 y equals to b, and we've got that a2 is different than 0, the solution, the particular integral, is b over a2. And look, this is a constant solution. So it means that the point that we are referring to is actually over time, and the value of y over time is not changing. So if I would like to draw this case for you, it would look something like this. That here is time, here is yp, and yp is not changing. It's simply always equal to the same value, b over a2. Okay, then we've got case number 2. In case number 2, we've got equation that looked like this: yb plus a1 y prime equal to b. So look, here we've got a case where a2 is equal to 0 and a1 is different than 0. So this equation has less components, right? And look how big of a difference it's going to bring. Because now, the solution, so the particular integral, is given as b over a1t. Look what does it imply? We no longer have a constant solution, a given number. This is a moving equilibrium. Our equilibrium is a function of time. And look, it shouldn't come to you as a surprise because we already did similar case when we were talking about first order differential equations. So you know that this possibility exists. So how the graph for this case is going to look like? So here we have time, and because, as you see here, we do not have any constant, we would draw it like that. Yeah, so with the time passing, of course, remember that this line can be also downward sloping. It all depends on the sign of b and a1, the same as this can be a negative solution. I'm just drawing it like that so you know what we're dealing with. Okay, and finally, case number 3. So in case number 3, our equation looks like this. Right? But because what we have here, a1 is equal to a2 is equal to 0. And what did we got over here? What did we get over here? yp is equal to b over 2 t squared. I hope at this moment you know where I'm going with this, and I need to have some. Okay, let's assume that we're dealing with this like that, because I need to draw a parabola at this moment. Okay, so here we've got time, here we've got y. How our function is going to look like? It's also going to be a moving equilibrium, but this time it's going to be a quadratic function. Okay, so now that we know all the three cases, let's just do 3 examples for each of these cases. But as you see, there's not much philosophy into it, and you just apply the formula for a specific case. Okay, so let's just say that we've got equation y bis plus y prime minus 2y equals to -1, right? In this case, clearly we've got, in this example, we've got case number 1. So particular integral is simply b over a2, which means that this is -1 over -2, which is 1 over 2. And this is the solution that we have. Okay, now what if now we need to deal with the equation y bis plus y prime equals to -1, right? So what do we do now? Well, this is clearly a case number 2, but an easy one, right? Because we've got here y, that yp, of course, is equal to b over a1t, right? We're using a second possible particular integral, which gives us that this is -1 over 1t, which is minus t. And finally, case number 3. So we've got equals to -1. What are we getting now? Of course, we apply the third formula. So we've got that this is b over 2t squared, which gives us, in this particular case, -1 over 2t squared. Well, as you see, the entire trick to finding particular integral in those cases is just recognizing which of the 3 cases are we talking about. And then we just apply appropriate formula that we already shown that is going to work. Okay, so this is it about particular integral. In the next video, we're going to move to the complementary function. Thank you for your attention.